Okay, so this talk will be by Sylvain Mounon, who works with the Osmocom project. He will talk today about the Osmo GMR satellite phones. After the talk, there will be the opportunity to ask questions. So you can approach one of the microphones and then you have the chance to ask one question. So please give a round of applause to Mr. Sylvain Mounon.
Okay, hi. Thank you for being here. So, as he said, I'm going to talk about satellite phones today. I'll first start with a quick recap of the previous work we've done. At 28C3, there was a presentation on this subject, but there were some pieces missing, and so I'm just going to recap what we did previously and then move on to the new stuff, which is the speech codec and the cipher reverse engineering and cracking that's been done. So first, what is GMR exactly? Well, GMR stands for Geo Mobile Radio, and it's an ETSI standard for satellite phones. It's heavily inspired from GSM, and if you read the GMR specs, there's plenty of reference to go see the GSM spec. There's actually two standards named GMR, GMR1 and GMR2. They are not evolution of one another. They're competing standards that have just been developed by distinct companies, and then both have been standardized through ETSI. Today we're going to be looking at GMR1. That comes in 3 evolutions. It started with just plain old GMR1, which is voice calls and SMS. It evolved to include packet data, and that's called GMPRS. And then there was a later evolution to interconnect with a 3G core network and improve the air interface and stuff like that, and that's GMR1 3G. But we'll be mostly looking at the first version, which is still used. Among the deployments, the one we focused on was Thuraya. The reason why is that it's the most common commercial operator where you can actually buy SIM and place phone calls. The satellites are visible from Europe, which is kind of a requirement for me to look at the signal. And this operator is mostly active in the Middle East, Asia, and Africa. In Europe, you don't see too many people with satellite phones just because we have GSM coverage. But there are other operators, and we actually read recently that there is a new deployment planned for Europe called Solaris Mobile, and they said they're going to use GMR1 3G, but the satellite isn't launched yet. So this is the coverage zone for Thuraya. As you can see, Europe is very well covered. So there's no problem if you want to receive the signal. If you're somewhere in that area, you can see it. So since it's so heavily inspired by GSM, it kind of makes sense to compare it to it. The first thing they did is they renamed everything. So basically, instead of a base transceiver station, you have a geo transceiver station. Instead of a base station controller, you have a geo station controller. Instead of a mobile station, you have a mobile Earth station. Then they did some actually useful stuff, like use specialized features for satellites. The first one is terminal-to-terminal calls. So when you're usually placing a call, the signal goes from your satellite phone to the satellite, then it goes back to the core network on Earth, and then if you're calling another satellite phone, it would have to again go back up to the satellite and back to the other phone. And that means that you pay 4 trips, from Earth to space. And since the satellite is in geosynchronous orbit, it's pretty far away. And so to kind of reduce the delay in communication, they have the so-called terminal-to-terminal calls where the core network will still handle establishing the channel and stuff like that. But once the call is established, the data is going to directly go from one phone to the satellite and directly back down to the other phone without any involvement from the network. It never even sees the packets. They also have this code called high penetration alerting. That's because, like in the movies, you see people using satellite phones, in bunkers and stuff like that. In practice, as soon as you're inside, you can't see the satellite and you can't place a call at all. But you still might want to be able to at least, you can't pick up the phone, but you want to know that somebody is calling you. And so they have this specialized channel which has incredible amount of error correction on it, so that even with very, very low signal, you can still get an indication, yes, somebody is trying to call you, please run outside so you can take the call. There's also a very tight integration to GPS. Like, for example, all the almanac and ephemeris data are actually broadcasted by the Thrive satellite so that your phone can get a log faster. And when you place a phone call, the very first thing that your phone will do is send your exact GPS coordinates in clear to the operator. And they do this for two reasons. The first one is if you're not on the right frequency for this particular geographic location, they can tell you, okay, you shouldn't be connecting on this frequency, use this one, it has a much better signal and you'll get better quality. That's one reason. The other reason is purely commercial, it's for billing, because like if you're calling while you're in certain country, it's gonna cost more than if you're on the other side of the border, and so they need to know where you are to bill you correctly. And then compared to GSM, of course, they introduced the two things we're going to look at today. Is they changed the speech codec to something called AMPE, and they changed the cipher. They're not using A51 or A52 or A53 or that kind of stuff. They use something called A5GMR1. So if you look at the protocol stack, anything in the lower layer, so radio modulation, TDMA frame structure, all that stuff, it's completely different because you have to deal with, the particular of the satellite communication. So you find the same kind of concept and you find the control channels and broadcast channels and that kind of stuff, but their implementation is different. If you go up one layer to the data link layer, you have something very similar to LAPDM. Again, they needed some minor adaptation because bandwidth costs a lot on the satellite. They reduced the size of the overhead by reducing the header. And since you have so much delay, going from your phone to the satellite, then back down to the Earth station, then again to your phone, you have something like, I think it's nearly 500 milliseconds of delay, because you have basically 250 milliseconds, sorry, because you have both paths up and down. And so with that delay, you need more time for the acknowledgement to actually come in and stuff like that, so they increase the window size. Anything above that, so layer 3, radio resource, since it's managed, the radio channel is still a bit different, but anything above that is strictly the same as GSM. It actually interoperates with the GSM core network, which means I can take my Belgian operator SIM, put it in a Turaya phone, and I can roam onto the satellite and place calls and stuff like that, which is really nice, except for the price you pay at the end of the month. For packet data, it's essentially the same thing. Anything that's close to the lower level, like RLC and MAC, it's going to be different. Anything above actually interoperates with GSM, so you're going to be speaking to a GSM core network and SGSN and GGSN and all that good stuff. So Osmo GMR, so what we presented last time, essentially everything you needed to go from RF to Wireshark. That includes the hardware setup, so how you can build an antenna, what LNA to use, what SDR receiver to use. At that time, we didn't actually have RTL SDR, which are the cheap DVB dongle you can use as SDR. Nowadays we do, which means that for like less than $100, you can get an antenna, LNA, and SDR receiver, and all the hardware you need to actually listen to those signals. Then we did all the SDR processing, which is taking that raw data, filtering it, selecting the channel, doing the demodulation, getting actual data bits out of it. Then channel coding, which is converting those data bits into layer 2 frames. Then interpreting those layer 2 frames into channel assignment and follow those assignments and that kind of stuff into a demonstration application. And finally, the Wireshark dissector, which takes all of this and presents it nicely in a way you can actually read stuff. But there's two things we couldn't do. Is first, we couldn't see past the ciphering mode command, which means as soon as ciphering was enabled, we couldn't see anything because we knew the key because, it was our own calls and we can read the key from the SIM, but we didn't know the algorithm that was used to cipher, so there was no way for us to decipher that. And we also had no way to get the voice data, converting the frame into actual audio that we can listen to. We couldn't do that, and that's what we're going to look into. So the first thing is the speech codec. It's called AMBE for Advanced Multiband Excitation. It's not a codec in itself. AMBE is not a codec in itself. It's more a family of codecs, which means you have several codecs which are named AMBE, which are actually different versions of one another, slightly different, so that they're not compatible. It's not documented in the standard, which is really annoying. When I started working on GMR, I really thought that the codec was in there. And when I discovered it wasn't, that was a bad day. There is a bit of specification in there, but it only gives a high-level description like, okay, the codec takes like audio as input and produce 80 bits of output every 20 milliseconds or stuff like that, but nothing that can be used to realistically implement a decoder. So that codec is made by a company, DVSI Incorporated, whose entire business is codecs. That's all they do. Basically, which is probably why there's different incompatible version of AMBE, is because they can sell different versions. These guys do sell like a small USB stick that can decode some of the variants. For example, you can decode D-Star audio, which is also another AMBE codec, or P25, which is used in law enforcement radio in the US. It's also an AMBE variant. And the cheap USB stick can decode that. Unfortunately, it's incompatible with the GMR1 variant, because that's the first thing I did is I contacted DVSI to know what were my options. And basically, short of buying a source code license, which is just too expensive, is buying the appliance, which is called Net 2000. And not only does it cost like €2,000, which is way too much for a hobby project, but you also have to special order it with a GMR1 firmware. And you have to sign some non-reverse engineering agreement and all that kind of stuff, which that wasn't an option. And we still had some hope. The first hope we had is that, as I said, P25 uses an AMB variant of codecs as well. And this particular variant is actually documented. So you can download the standard for that particular variant of AMBE, and you have all the math and all the specs, so you can write a decoder, and somebody actually wrote a decoder which is open source, which is called MBLib, and so we could use that code as a base, possibly to modify it or something. So that was a lead. The other lead, of course, is that the codec is somewhere in the phone. The phone is obviously capable of decoding audio, so maybe we can find it in there. But before we can start, searching for the codec, it's good to have a basic understanding of how the codec works so that we know what we're looking for. The first thing to understand, it's a vocoder. It's not a general purpose audio codec, which means if you try to feed it music or stuff like that, it's going to perform horribly. Because a general purpose audio codec will try to model what your ear can actually hear and what it can't. While on the other hand, a vocoder is going to try to model the speech and reconstruct something that sounds like, but is not actually the same thing. Like they will drop a lot of information. To do that, the first thing they do is they split your speech into small segments, which are compressed independently. In the case of GMR1, those segments are 10 milliseconds long, and they're combined by pair, and each pair is compressed into a single frame. And then for each of those small segments, they will represent it in 4 parameters. Those 4 parameters are the pitch, which is essentially the fundamental frequency at which of the periodic component of your voice, if you will. The gain, which is how loud you're talking, of course. Something called voice and unvoiced decision. We're going to see what is this right after. But essentially, you have the fundamental frequency, then for each harmonic, so 2 times the frequency, 3 times the frequency, 4 times the frequency, you have a bit that says, okay, is that component voiced or unvoiced? And then you have the amplitudes for the various harmonics. And so you have those parameters, and if you want to actually play back the voice, you have to do 3 things. The first thing is unpacking, and that's taking the 80 bits of the voice frame and reconstruct a quantized parameter from it. So all the parameters are not just put in order one after the other, because some of the bits in a frame will receive more error correction than others, and some of the bits are more sensitive to errors than others, and so they will be placed at specific places in the frame, so that if error do happen, hopefully it will affect something that is not too important. So that's the unpacking step. The second one is dequantization, and that's going from those quantized, compressed parameters into actual, floating point value or integer values, which represent the real parameters that can be used for the last step, which is synthesis. And synthesis is, taking those parameters and reconstructing, actual audio that sounds like the original voice. And so to do a quick overview of the synthesis step, what you do is you take, for each possible harmonic, so F0, 2F0, 3F0, you have the voiced and unvoiced decision, and what voiced means is that you're going to reconstruct that particular frequency as a pure sinusoidal tone, and if it's unvoiced, you're just going to fill that small band with noise, essentially. And with that, they can actually reconstruct human voice pretty well. So, now that we know more or less how the codec works and what we're looking for, we can start looking at, where are we going to find this codec? The phone we looked at is the Turia SO2510. And we looked at it mostly because it was the cheapest phone on eBay. And that also means it's the simplest, which means you have less places to look into. Now, we knew it was the codec was in the DSP, and how did we know that? Is that there's simply no other places it could be. There are a bunch of chips on that phone, of course. There's only two where it could possibly be. Is the TI OMAP main processor, and then they also have like a small ASIC, which is named the Dalma ASIC because there's a big Dalma marking on it. And at first, we actually thought that that chip was the AMB codec. But it turned out that we found some Korean paper from the phone manufacturer that described their phone architecture, and they actually had a schematic of the internal of that ASIC, and it showed that it only had like satellite radio functions and absolutely nothing to do with the codec, which means there was a good chance it was in the TI OMAP processors. And why in the DSP? Well, because it just makes sense to make the codec in the DSP, especially since DVSI, the company that actually makes the codec, mostly sells those codec as DSP precompiled library that you can buy. So, pretty standard process. We get the firmware update from the internet. From there, we can extract an actual DSP image, which is the code which is loaded in the DSP. Thankfully, it's supported by IDA, which makes the whole process easier to reverse engineer. But it's still like 250 kilobytes of binary data. And since it's the DSP, it has no I/O, which means there's not a single string in it. And also, it's a DSP, which means it's written in DSP assembly. And I don't know if you've ever tried to read that, but it's not the most understandable thing in the world, because it's highly optimized for speed, of course. And I actually looked at that code and went over it a few times and took a few hours and looked at it, and I couldn't see anything in it. And one day I get an email from a colleague in Osmo.com, Dieter Spar, asking me, if I had ever looked at that codec, and I told him, I looked, but I couldn't really find anything. Do you see anything? And like 6 hours later, he sent me, I think this is the entry point for the encoding and decoding functions. Okay, good. And the way he found that, essentially, at least from what I remember, is that you look at what would a codec use, and of course, it's gonna access the audio path, so you can look at the audio DMA setup and audio DMA interrupts. You can also look for constants that are used in the codec. So, for example, I said that the frames are 80 bits, so you can look for the constant 80 somewhere in the code. You can look at it. It will produce, I think, 160 samples per audio samples per frame decoded. So you can look at the constant 160, that kind of stuff. And once you actually found one function, there's something that kind of stands out, is that since they ship that as a binary library, they don't really trust the guy who implement the rest of the DSP code to set up the C runtime properly. And so what they do is they switch everything at each call into the codec, is that they switch the stack and they reset up, reconfigure the C runtime and that kind of stuff, so that it's really independent. And so once you find one function, finding the other is pretty easy, because you can just look for that particular function, how is it called, prelude or something, that happens at each call at the audio library. Okay, so we know where the code is, but it's still a massive amount of code. I mean, I think it's like 1/3 of the DSP code is the audio codec. So it's not something you can easily reverse engineer in a few hours. So before trying to actually reverse engineering, we just tried, okay, maybe we can just run it. It turns out that TI has this really nice program called TI Code Composer Studio, which includes a simulator. And it's a really nice piece of software because not only can you pretty accurately simulate any of the DSPs, you can also completely configure the surrounding environment in which it runs. So you can set up arbitrary memory map. You can also trace all memory access to see what part of memory is being read or being written or being executed, that kind of stuff. You can also actually access file on your host file system. So you can use fread and fwrite, and the simulator will automatically translate those calls into actual reading from your hard drive and write to your hard drive. So you can just read a compressed file that you saved, and it will write an audio wave file at the output. And the way to do that is pretty straightforward. I mean, you essentially just need to take the binary dump that you have from the firmware update, and you need to find a way to mix in with your own custom code. The way to do that is basically you just create a new object file, like you would create an ELF, except in this case it's called a COFF, for a common object file format. But it's the same idea, and then you can just link to it like you would link to any piece of other piece of binary. You write a simple main function that will basically, fread your compressed samples, call you the decoding function, or at least what you hope is the decoding function, and fwrite the audio samples. And surprisingly, it actually worked, and it worked pretty. It didn't require that much effort. I think in like a couple of days, it was all working. It didn't work on the first try. There was a couple of pitfalls and stuff like that. But essentially, the idea is there, and that's probably something that can be applied to other things as well. Of course, there's some pretty big downside. Is that first, it's pretty slow, definitely sub-real time, even on a modern laptop. It also requires a TI Code Composer Studio, which is a Windows application, and it's also not free. So you have like a 30 days evaluation period, but that's about it. So it's really not that practical. But I mean, it was running in the simulator, so there's no real reason it can't run on real hardware. So of course, that's what we try next. Now, unfortunately, on real hardware, you can't just put memory anywhere you want. When the codec runs in the phone, it actually runs inside an TI OMAP, which is an ARM plus a DSP, and that chip has an MMU, which means you can create any virtual memory you want. But if you're trying to run on a cheap DSP board that you can get for like $50 or something, those usually don't include an MMU at all, which means you need to find a board which has memory at the right places, because the binary you have, it's been linked to a specific physical address, and it needs to run at that particular addresses. Thankfully, Dieter found one such board with a compatible memory map, and it had a SDRAM where we needed it to have some memory. It also included Ethernet, which means we can make some networked appliance where we submit samples and get them back and that kind of stuff. So that was really nice. And the process of migrating the code from the simulator to the board is actually pretty smooth because of the way the Code Composer Studio works. You just basically select another target, and since the memory was at the right place, it pretty much worked. Now, it wasn't quite as fast as we wanted, because it was only about running about real time at the first try, and that's because SDRAM is slow, especially when you do a bunch of random accesses. The SDRAM isn't really fast. And the codec, unfortunately, has a lot of big data tables which are accessed constantly, like to compute cosinuses and stuff like that. So what Dieter did is basically, identify a couple of those big tables that are accessed very often, and then just migrate them to internal SRAM. You just find one or two places where the code reads from those tables, and just patch the address to another address and redirect it to there. And that got the code running much faster, about 16 times faster than real time. And honestly, that was good. I wasn't really planning on doing anything else on the hardware, and so I ordered the same board, except I didn't. I somehow ended up clicking on the wrong button at the iStore or something, and when the board arrived, I didn't have the right one. And at that point, of course, I had two choices. I could just order the same board and just wait one more week, or I could try to run the code on it anyway. Now, the second board didn't have Ethernet, it had USB, but most importantly, it didn't have any SDRAM at all. It only had internal SRAM, and unfortunately, not at the right address. So I just figured, okay, I'm just going to try to relocate the binary and make it run at another address. How hard can it be? It turned out to be pretty straightforward because, I mean, I think in less than a day it was running, and that's really thanks to IDA Python and the simulator. Basically, what I did is in IDA Python, which is the scripting language for the IDA, reverse engineering software, you can basically, iterate through all the opcodes. Then for that opcode, you test, okay, is there an absolute memory reference somewhere in that opcode? If no, well, then don't do anything. If there is an absolute memory reference, is that reference falling somewhere in a place that I'm trying to relocate or not? If it is a place I'm trying to relocate, then just patch that opcode and change the absolute memory reference to, well, the new place. Go through all the code like that and try to run it. Now, of course, that didn't work the first time around because there is a couple of pitfalls in that approach. But using the simulator, it was pretty easy to find out where things were going wrong because you take the original code, you run it in the simulator, and you trace every memory access. Then you take your potentially relocated code, you run it again in the simulator and trace every memory access. And I mean, you're decoding the same frame, it should be determinist, and so you should have the exact same memory access patterns in both cases. And as soon as you see that they're diverging, you know that somewhere a branch wasn't taken or something went wrong, and you can go at that place in the code, look, and see why the relocation didn't work. And it only took, I think, 2 tries or something to have the code running, and it was running on my board, and I didn't have to order a new one, which was pretty nice. So we have a hardware USB decoder, which is, very useful, but you still have to carry it around or have it plugged on a networked server or something, which isn't necessarily something you want. So I wanted something I could check out in the Git, basically. So I started reverse engineering the entire codec. Now, it turned out to be very painful. As I said, to reconstruct audio, you have 3 main steps. The first one is unpacking, and it's just basically bit shuffling. This is like the first thing the codec does, which means it's really easy to find, and it's really easy to follow, so no problem there. The second step is dequantization. And that took like 95% of the work because it's a lot of math. It's all written in DSP assembly in fixed points. And sometimes you're looking at a function, and to figure out what that function does, you basically have to run it with different parameters and stuff like that to see what does that thing compute. Graphing is really useful for that. You just feed some inputs in the simulator, see what output is generated, and just plot it in PyLab or something. And then you can see, oh, okay, so that actually computes a logarithm or something. So, but I mean, there's still a lot of code there, and there was no other option for that part because the quantization step is completely specific to GMR. It's not shared with any of the other AMB variants. The synthesis part is even more complicated. It's even more more code in the DSP, but I really didn't want, after finishing the dequantization, I really didn't want to do the synthesis. So I just kind of assumed that the synthesis step was going to be very similar to the one in P25. So I took the MBLA existing open source code for P25. I ripped out the unpacking and dequantization out of it. That's because it's the one for P25, of course. I just plugged my own implementation and run it through the synthesis. I mean, it's not, there's a couple of things you need to take care of, mostly because P25 uses 20 milliseconds frames, GMR uses 10 millisecond frames, so I basically dropped one frame every other frame in GMR and just used the 10 millisecond parameter to synthesize 20 milliseconds of speech. But it produced something where you could follow a conversation, and it worked. I was still not really happy about it because the code quality of MBLib is really not that good. Its performance is also not that good. It wasn't actually faster than the hardware decoder. So in the end, I just went back to the actual P25 specifications that I had and rewrote a clean implementation of the synthesis step. I just guessed the difference, basically. Every time it says 20 milliseconds, I just put 10 milliseconds. When there is a 512-bin FFT, I just put 256, and adapted stuff as I went. And the resulting code is in the Git, and you can decode voice. It works. I think it works pretty well. You can hear some subtle difference compared to the original codec, because DVSI they do a bunch of stuff to improve the voice quality. I mean, it's the whole business, and I didn't go through all of that. But there's, I mean, from my point of view, I'm done on this. I'm not going to go any further. We have C code that we can run, so that's good. Thank you. So next we move on to the cipher. Now, we didn't reverse engineer the cipher. That was done by a team at the Bochum University, led by Benedict Drissen. Right after after 28C3, basically, actually at 28C3 we already had some contacts with them, but the paper wasn't published yet. And we actually helped them validate their data and their attack using Osmo GMR. I definitely encourage you to read the paper that they published, because the method they used, they are actually the one who extracted the DSP image, which we used to reverse engineer the codec. They were the first one to extract it from the file that you can download online. And then there's some pretty interesting stuff in there. As I said, they also published an attack on that cipher, which is a ciphertext-only attack, and I'll show some of the results later on. So, what does the cipher look like? Well, it looks like that. If you're familiar with A52 or even A51, that should look very familiar, because it's pretty much the same thing. So you have 4 linear feedback registers. The first 3 ones are combined using a nonlinear output function into the actual key stream. And then you have a 4th register, which a few of the bits are tapped. They go through a nonlinear clocking function, and that function is going to determine how fast the other registers are clocked. So not all registers advance at each output bit. And as I said, it's very similar to it's actually a copy of A52, except they change every number. Like, they don't, the polynomial for the linear feedback registers are different. Which bits are tapped to combine into the outputs are different. Same thing for R4, but it's the exact same structure, which means we can reuse the attacks that work on A52. This cipher obviously has an initialization step, where you basically take the key and the frame number that you want to encrypt, and you have some process to initialize the LFSR with those data. But really the only thing to retain is that this initialization process is entirely linear. There's only XOR and LFSR being involved. So that's pretty much the thing to remember. the actual irregular clocking only is applied when you generate bitstream for encrypting the frame. Now, since we're going to talk about attacks on ciphers in some details, there's a few things that you may not remember if you don't do algebra all the time. And so this is a very, very quick reminder. So what you know is that when you see GF2, that's just a fancy term for binary. What we call addition in GF2 is just the XOR operation. The multiplication is the logic AND, and you can do everything with that. And if you accept those definitions, then algebra over binary is going to behave pretty much the same as algebra over real numbers and stuff like that, and all the nice properties are going to be applicable to binary math as well. No, I mentioned previously linear, and I will mention it several times in the rest of this talk. When I say linear, it's basically, it's either a constant or a variable or unknown multiplied by a constant. But you never have two variables multiplied together or that kind of thing, because then it becomes quadratic and it's not linear anymore. Being linear has some very nice properties, like linear systems of equations. We have very fast algorithms to actually solve them. And every linear operation can be represented as matrix operation, which is especially useful if you're dealing, we're going to be dealing with hundreds of unknowns, and just spelling them out is not an option. We have to have some way of representing that, and that's matrix operation, essentially. One other important thing to know is when you have an operation that adds redundancy, for example, channel coding, where you add a CRC, or where you do convolutional coding, adding error correction adds redundancy to your message, essentially. And when you have redundancy, you can actually create what's called a parity check matrix to check if that redundancy is indeed present. So for a CRC, it would check the CRC, for example, but it can be generalized to anything that adds redundancy can be checked. And that becomes very useful to make the attack much faster. So a little more detail about what the guys at Bochum did. They published a ciphertext only cipher. That means you only need to capture data of the air, and directly with that you feed it to the attack, and it can give you the key. They target what's called TCH3 frames, and those are traffic frames. They're basically what carries the voice, which means you have a lot of them, because as long as the conversation is still going, you have frames are being generated constantly, several tens of them per second. No, they didn't start from nothing. As I said, the cipher is heavily based on A52, so it kind of makes sense to read the papers that were published about A52 attacks. The most interesting one, and one of the most advanced one, is called instant ciphertext only cryptanalysis of GSM encrypted communication. It's kind of math heavy, but it provides an attack on A52 that recovers the key, as I said, instantly, which is really nice. But they actually modified this attack. They tweaked it for GMR1 because, the frames are different, there's different number of bits, the cipher is slightly different, and that kind of stuff. And they also did something a little weird, is that they tried to guess more bits. Some of the bits, they basically tried to brute force them. I'm not exactly sure why. I think it's to reduce the number of unknowns, but I don't know if that actually had the desired effect. And in the RUB paper, they published their result, and basically with 350 gigabytes of pre-computed data, using 32 TCH3 frames, they managed to recover the key in something like 40 minutes, which is not bad, definitely, and it works. But the original attack is named instant. 40 minutes isn't instant, to me at least. So we started looking for a better attack. Now, we started off the same paper, essentially, because it's kind of the state of the art for A52 attacks. But we really didn't do anything fancy. We just used it exactly as they said in the original paper, and we just did the necessary tweak for A5GMR1, which is changing the matrix and the length of the vectors and that kind of stuff. Really nothing fancy. We also decided to attack a different type of channel, and this is probably what makes the most difference. Is we decided to target FACCH3 control frame instead of the TCH3 voice frames. Now there is a very big advantage to targeting those frames. First, there's different kind of modulation and training sequence. And from an RF point of view, they are much easier to receive. And that's pretty important if you're trying to mount an attack, because as soon as you have a bit error in the reception, it will basically make your equations inconsistent and you won't actually be able to solve for the key as easily. So these are very nice properties of those frames. The other very nice property is that we have known plain text on FSCH3 channel, on the control channels, there's some very predictable frames that we know will be there and we know where they will be. The voice traffic is completely unpredictable, it's someone talking. The control traffic will follow some very known patterns, and I'll show some example of plain text, which is really trivial. Some other of the nice properties of the control channel is there's much more redundancy. In TCH3, not all the bits are actually error corrected, which means you don't add that much information. While for the control channel, each layer 2 bit that you transmit is almost quadrupled before you put it on the air, which means you can build a lot of equations very fast without many bursts. In the RUB attack, they needed 32 frames. That's probably because there is not that much redundancy in the TCH3 frames. And also, as a nice bonus that we discovered later, is that the FSC, that control channel, is also used to negotiate other types of channels, like the channels that are used when you send fax or when you send when you establish a data call over the satellite networks. It's actually negotiated using that type of control channel, which means the same attack can actually work to crack not only voice calls but also data calls and fax. So this is an example of the plain text. I don't know if you can really see, but essentially on the top you have the cipher mode command. The first line in blue is the cipher mode command. So everything after that is in theory ciphered. Of course, it's the unciphered view. And the 3 marked packets in gray and black are the very predictable text. And what they are is basically just acknowledgements. Because of the delay on the GSM channel, there is some outstanding acknowledgement that still need to be sent once the ciphering is turned on. And so you get basically empty packets with just incrementing sequence number and the ACK bit set. And so something changes in them is the sequence number, but you just, as long as you can count, predicting them is trivial. And this definitely works in practice like 100% of the time. Never really had any problem with that. Okay, so how do you build a plain text attack? The general goal is what you're trying to achieve is build a giant system of equation that's linear and that you can solve. And it's going to have the form A multiplied by X equal B. B is the cipher stream that's generated by A5GMR1. X is some representation of the internal state of the cipher that you're trying to find. And A is a giant matrix that you can pre-compute that's only dependent on the structure of the cipher, essentially. And each row of A and B are going to basically represent 1 bit of the output and how to combine that internal state to generate that cipher stream bit. Now, as I mentioned, the initialization process is linear, and that's very important for 2 things. Is that first, from the internal state of the cipher, you're going to be able to recover the key, which is actually not entirely true. There is 1 bit of the key that you can't recover because that bit of the key turns out to have absolutely no effect on the output whatsoever. So you can't recover it, but it doesn't matter either. So, and the other thing is that you're going to need to build a lot of equations. That system is going to be big. And in a single burst of data, you won't have enough equations. You're going to need multiple of them. But of course, those multiple bursts are going to have different frame numbers because they're sequential. And they're not going to wrap before a long time. So, but since the initialization is entirely linear, you can actually derive equation from one frame number from equation built around another frame number. But of course, it would be too easy. The cipher isn't entirely linear. So we have to linearize it. And When I first started looking at crypto attack on A52, in the papers it was always one line that said, oh yeah, we linearize the cipher. And they kind of always assume that the readers know what that means, which I didn't at the time. So I decided to be a little more explicit. So the two nonlinear elements are the output function, which uses a majority function where basically you take 3 bits and it outputs the whichever bit is more common. And you can rewrite that majority function as being the sum of A plus B multiplied by C, or if you wish, eggs or B and C. And the problem is the B multiplied by C, because that's quadratic, that's not linear. That means that we can't introduce that. And the way to linearize that is basically to kind of ignore it. For every possible quadratic term that's going to be generated by that nonlinear output function, you generate a new unknown. I mean, in reality, that unknown isn't really unknown. It's kind of a function of your other variable, but you can't represent it in a linear fashion. So you just ignore it and just say, okay, this is a new unknown, and deal with it. And for it, there's a lot of possible combination, which adds 594 new unknowns to your equation systems, which means you're going to need a bunch more equations to be able to actually solve it. But at least it makes it linear, so there is hope. The other, nonlinear thing in that cipher is the clocking. As I said, all the LFSR don't advance at the same rate. Some are clocked once or 0 time at each output bits, and this is a function of the actual value of R4 at that particular time. So how do we linearize that? Well, R4 is a 17-bit linear feedback register. So we can know all its future state from any, I mean, as soon as you have a bit state at one particular time, you can predict all the future states because it's clocked all the time. And in those 17 bits, the initialization step actually forces one of those bits to 1. So there's only 16 bits that you don't know, which means there's only 65,536 possible clocking pattern for this cipher. And so the way we approach that is we just brute force it. You just assume that R4 is going to be equal to that value after the initialization, and you just assume that and try to solve and crack the cipher by using that assumption. And if you find a KC, well, then maybe it's the right one. You just repeat that 65,000 times, and most of the time, if your guess about R4 isn't correct, the system will end up being inconsistent, and you won't actually have any solution. But I mean, this kind of still requires solving 65,000 systems, which is, fast, but not that fast. So there is actually a trick that we can apply to do better guesses. When you build these giant equation systems, it turns out that some of the equations that you construct, they're not going to be independent. Some of them are going to be related to each other, and so some of the rows are redundant. And what's nice is, if they're redundant, we can actually test for that redundancy. And so for those 65,000 possible systems that you need to solve, so you have an multiplied by x equal b, there's a bunch of rows in an that are going to be linearly dependent. So for each of them, you can build a parity check matrix, HN, so that you have this nice property of parity check matrix where you multiply b by HN, and you get a 0 matrix. But all those HN, you can pre-compute them. That's essentially the offline data of the attack. You pre-compute those giant matrices, and then you take B, which is the ciphertext you got from the cipher. You multiply it by this matrix, and if it gives you 0, you know that this particular R4 value might be correct. You don't know if it's correct or not, but at least it might be. If the result is non-zero, then you know that R4 is definitely not the correct R4. And so instead of solving an entire system of equation, the only thing you need to do is do one matrix multiplication, and that is pretty fast. And in the end, you're going to have a couple of possible matches, so you're going to solve like, maybe 3 or 4 system of equations instead of solving 65,000, and that's much, much faster. Now, how do you go from known plain text attack to a ciphertext only attack? Yeah, I'm not going to detail that much, but essentially, the channel coding operation introduces redundancy, and you can kind of null out that. If you take the last equation, you have h multiplied by y plus g. H is a function of the coding, channel coding. You can compute it; it's known. Y is the data that you've received off the air, so you know it as well. G is also a function of the channel coding operation, so you know it. So everything on the left, you know, okay? And the last value is h, which, well, you know it. Again, it's the same h multiplied by a, which is what you had in the known plain text attack, so you know it as well. And the only thing you don't know is x, and so, again, you have a linear system of equation that you can solve, and the same for quick scan method can actually be applied to scan very quickly and not have to solve everything. So this is the result. I mean, essentially, if you actually use the fact that you know some plain text, you need about 50 megabytes of data pre-computed. You need to receive 8 bursts, or even 4 if you just by any chance have the right frame number alignment. And in like 500 milliseconds, you can get the key back. And that's on a 6-year-old laptop. I mean, on any recent machine, it's really no instant. If you want to use the ciphertext only variant, and honestly, I really don't know why you would, because the known plain text just works, so you might as well use it. But if you want it, purely for academic purposes, then you need, 8 bursts, about 5 gigabytes of data, and then it takes a little longer, like about 1 second to recover the key. So, few things we'd like to look at in the future is C-band. So, the satellite has to talk back to the Earth station, and this happens in a different frequency band, and this is what we'd like to look at, essentially the feeder link. If any of you have a large dish, satellite dish, and want to provide data for us, please contact us, we're looking for it. We're also starting looking into packet data, and some other stuff. Yeah, a quick note about other satellite phone systems. Please don't assume that just because Thuraya or GMR1 is broken that the other aren't, unless you have actual proof that they aren't, because the only reason we chose Thuraya is because the phone was the cheapest on eBay. So given that other satellite phone systems also, you can find commercial interceptor for them, there's a big chance that, they're not that much more secure. So I'd like to thank a few people, Dimitri Stolnikov for the main other author in Osmo GMR and doing a bunch of the RF capture stuff. Dieter Spar for reverse engineering of the AMB codec and all the help he provided there, and the RUB team, of course, for their support in reverse engineering the cipher, and the organizer for having me, and thank you for your attention.
Yes, thank you very much. We now have time for a few questions. First, are there questions from the internet? Not yet. So if you have a question, please approach one of the microphones. Yes, please, microphone number 3.
Okay. Yeah. Yes, I have a rather not technical but political question. So you said in the beginning there was like a short way of communication that only the satellite transmits the voice data, so there is no ground station involved.
Yes.
Do you think that this might upset some of the people who like to intercept calls, because it makes intercepting the voice data much more complicated than just going to the ground station and say I want to listen to this?
First, just because the satellite will send the data back directly to the mobile phone doesn't mean the satellite can't also provide a copy of it to the Earth station. It just doesn't go through, but the satellite can obviously send a copy of it if they want to.
And probably there will be a possibility for the ground station to say, don't do that direct connection, probably.
On the other hand, they can also just intercept it off the air because it's so easy to listen to it. I don't know if you see, last year there was a talk with somebody that looked at satellite pictures, and they saw that one of the spy satellites was relocated like right next to the Thuraya 2 satellite. So you can look that up. It was a presentation last year. It was pretty interesting to see that, if they want to listen to it, they can do it, even without the
Thank
you.
Next question from microphone number 2.
I have two questions. Can you hear both sides of the conversation or only one side of the conversation? And the second question is, how big of a dish do you need?
Okay, so if you want to receive L-band, which is just listen to communication from the satellite to the phone, you don't need a dish, you need like a small antenna. You can even do it with a modified GPS antenna and a piece of metal. So it's really easy and really cheap to do. You can only hear the part of the conversation that comes from the satellite to the phone. So if by any chance that guy is speaking to another phone, you can hear both sides just because you can intercept both channels simultaneously. But in general, you either only hear one side, or you can also be close enough to the actual satellite phones to receive the uplink that goes from the phone to the satellite. If you look at, Dimitri showed me like a commercial intercept system where apparently they use like planes to intercept the uplink, and so they just fly over the area of interest, and so they can more easily receive the uplink from the phones.
Okay, one final question. Please make it short because we are running out of time.
I'll try my best. Launching your own satellite certainly is not an option, but do you see any practical applications in terms of what you did with GSM?
Not really. I mean, it'd be interesting to try to start a net, because there is nothing that says that you have to be on a satellite. You could technically start a base station on Earth using that protocol, and it would work. And the phones have much more power than a GSM phone. But other than that, I mean, you could build an IMSI catcher for satellite phones if you wanted to. And you would definitely beat the signal strength of the satellite with your own setup.
Thank you.
Okay, so please give the speaker another round of applause. When you leave.
Thank you.